in this session, we're simply going to discuss proteins, and by the time the session is done, we should be able to define what proteins are, and also the forces that help proteins to be stable, and also what can damage the nature of proteins, that's denaturation. And also we need to talk about certain examples, or rather the functions of proteins, and the most important one that we're going to give as an illustration is hemoglobin, which is responsible for the transportation aspect of proteins, and also the misfoldings of proteins in terms of them unwinding back to become simpler amino acids. Because after we define proteins, which are simply, these guys are polymers, right, made up of amino acids, we can complicate the structure by coiling up the amino acids to form the following type of levels of proteins, either primary, secondary, or tertiary, or rather quaternary, depending on what you have. So here I gave a very typical simple illustration to say we have the primary structure, which is just a sequential arrangement of the amino acids. Then if you curl them up a bit, you form the alpha and the beta helix, you can create a secondary structure. You fold them further, you can create a tertiary structure. Then later on you can even get a quaternary structure. We'll go into the details of how these structures are going to be distinguished from one another. And to dive into what proteins are, we're just going to say proteins are simply, these are simply structures that are made up of amino acids. That's what we need to know. That's the basic definitions. So the monomers that make up proteins are simply amino acids, and these can be joined via a condensation reaction where a water molecule is always given out. Now we'll discuss, we'll give illustrations. For the basic sake, we're just saying the weight of proteins, a normal protein, the weight should always be greater than 6,000 atomic mass unit. A perfect illustration is hemoglobin, whose molecular formula you can see right here. This is a very long structure. This is sulfur, this is iron, there are 4 of them. So when you are done calculating the meter of of hemoglobin, it's simply going to give us 65,000 atomic mass unit, roughly. This is what you get. So these are going to be very dense type of biomolecules. So these guys are very important because of the following functions. So they have so many applications in terms of why we need them as humans. The first one, if we were to just categorize them, is called the catalytic function. So according to the nature of enzymes, remember under the study of enzymes, we said enzymes are protein in nature. Of course, these enzymes that we are discussing are synthesized in the body, right? So we're saying nearly all enzymes are protein in nature. So this is why we need proteins. The other reason is because we need structural support. So for structure purposes, so say the structural function, especially in mammals, the structure materials other than inorganic components of the skeleton are simply proteins. That's basically what you have. Yeah, so here we are saying enzymes in your saliva, stomach, and small intestine are proteins that help you digest the food. That's basically what we are saying. Then cellular construction workers in terms of them offering support, mechanical support. So that's what you basically have. Then the next other function that you can take note of is storage. So some proteins provide a way to store small molecules or ions. So we can store them either in terms of proteins, or proteins can be used to shield whatsoever that you want to store, either ions or anything else that is needed to be stored. Yeah, then the fourth reason is we can talk about the protective function. So the protective function can be in terms of antibodies. We can talk about antibodies. We are saying antibodies are proteins that help defend your body against foreign invaders, such as bacteria and viruses. Yeah, so this is a typical illustration. We're just giving a name to each of these purposes. These are illustrations of why we need proteins as humans. Then the fifth other thing that we can mention is in terms of movement and transportation. So transport, hemoglobin can come into that. So transport, we can give an illustration of hemoglobin. Then sixth, We can talk about movement. This is going to have to do with muscles, contraction and relaxation. So muscle proteins called actin and myosin enable all muscular movement from blinking to breathing to rollerblading. So this is basically why we need proteins. And also the last one, the seventh reason or function of protein is simply the nerve impulse transmission. So some proteins act as receptors for small molecules that transmit impulses across the synapses that separate the nerve cells. Communication between cells, right? That's a reason why when you step on something that or that is hot, or rather something that is piercing you, you're able to respond fast, right? Because of the movement that you're going to have. So there's a coordination in all these functions that we are discussing. So these are some of the important factors that you can consider in terms of us discussing proteins. Now, these proteins that we're going to be looking at can be classified into two groups. So the first group is us discussing the ones that are in a state that is a fibrous state. So we can either have a fibrous type of protein. So we say fibrous, we have fibrous. So these are simply going to be, the first thing that you can just talk about here is that these guys are insoluble in water. So insoluble in water. Why? Because they're made up of long rod-shaped or string-like molecules that can intertwine to form strong fibers. So this is basically what we're having. And the major components of connective tissue, elastic tissue, hair, skin. Perfect illustration can be collagen or elastin or keratin. So the keratin with K. So this keratin, the one that is found in nails, right? Yeah, so this is what we call the fibrous type of proteins. So these are naturally insoluble in water. Then the other type of proteins, we can just say, we can have globular proteins. So these guys dissolve in water or form stable suspensions. So these are made up of spherical type of shape. So these are spherical in shape and they are soluble in water. Perfect illustration is hemoglobin. That's the best example that we can give for globular like proteins. Yeah, so we're just saying proteins can take any of these two shapes. It can either be fibrous like a fiber, or it can be in a globular shape. So aside from the two groups of proteins that we have, we need to talk about amino acid, which is simply going to be the monomer that we're going to be using to produce any type of protein that we need. So the arrangement of the amino acid is going to co-upon or determine the function of the protein that you are having. So every amino acid has two types of groups. There is this carboxylic group on this side. So this is the carboxylic part. The acidic part, so just say the acidic part, it has an amine part or the amino part. So this is the amine. There is a side chain here which is called the ara group. So they are always going to be distinguished based on the ara group that they are having, but the terminal, this guy here is called the carboxylic terminal on the other end is called the C terminus. So some people say this, then this is called the N terminus, the amino side. Yeah, because it's an amine, so N. So this is the N terminal. This is what you'll be having. So all these are simply going to be the units needed for proteins to be made. Whenever a protein has less than 30 amino acids, we simply call that particular protein to be a peptide, because the bond created in the condensation reaction of amino acids connecting to produce these proteins, these are called they're going to be called polypeptide bond. So if I may give you a simple illustration on how the whole condensation reaction happens, regardless of the ara group that you are having, yeah, so we don't really care what ara group you are given. So since they are all differing here at the ara group, this is I'll say NH2, this is what you're having. This is this is here. There's another amine here, so there is H, this guy there. There's another ara group, so I'll just differentiate this by putting this apostrophe here to say, just say they are different. These aras are not the same. The ara here is not going, let me put a star. The ara here is not the same as this ara, because this can be from different long other monomers. So this is going to be, let's say, something like this. So if you react these two, we're just saying get this and get that to produce the water, meaning you're simply going to have carbon 2, the R, this is the hydrogen, this is the double bond there, connect them with the nitrogen with the hydrogen there that remains. Then this contains this other R group. This is simply going to be your dipeptide, because we just joined two amino acids, right? So this right here is what you call the peptide bond, this guy that is created here between two amino acids. Yeah, so that's what we have. Now, this sometimes can be written, or rather can be said, can be called to be Zwitter ions. So by Zwitter ions, we just mean that the carboxylic group that we are having here has the possibility of losing the hydrogen and become a negative charged particle. Then you have the R group there, we have the hydrogen there. Also this side, it has the ability to gain that hydrogen that was lost this side, and now it becomes partially positive. So this is what we call a Zwitter ion. Yeah, so this is what we mean when we say it has the ability to give us this. It's a double ion type of arrangement in this amine, in this monomer. And maybe to just mention one other thing, you have the most common 20 amino acids that you need to know are 20. So they will always give you a list of these structures. So if I may just use the Yoshihata notes here to show you these amino acids. There are 20 of them, and just for the sake of you knowing this, so this is the best picture I could find. So this here, there's lysine, there's valine, phenylalanine, there's glycine, there's arginine, there's cytosine, then there's glutamate, there's leucine, there's alanine. So there are about 20 of them. Now you don't have to master all of them, yeah, because they'll always give you a genetic code sheet that is going to have all the 20 listed. The only thing you have to be doing is identifying a particular protein that is called when a certain arrangement or sequence of these amino acids is given. So what I mean is, if you arrange, so these are shortcuts, these are like the acronyms for lysine. We just use LYS. So now if you arrange lysine, so if let's say you have lysine and we call them in a certain order, let's say you have your lysine, let me just put LYS, you arrange it with, let's say, valine and also glycine. So this sequence that we are having here, the arrangement of these amino acids, will call for a certain type of protein, right? That's what I basically mean. If you change this arrangement, if you say glycine, then valine and lysine, there's a different type of protein that you're going to call, or summon, so to say. Yeah, so the sequence matters, and we're basically saying amino acids are always going to be the monomers that are necessary for us to produce proteins. That's what we're basically saying. Yeah, so if you have 20 amino acids, meaning you can have how many combinations? For those that are doing math, meaning from the 20 you can just say how many ways can you arrange 20, right? You can either say 20 factorials. So you can have those number of computations that you can get when you switch these 20 amino acids. So just a takeaway here. So note that some amino acids are going to be said to be polar, and some amino acids will say to be non-polar, and some of these R groups that they'll be placing here, because we are saying all amino acids look the same, except they only differ at the R group. What is going to be differentiating them is the R group. So if you have a lot of hydroxyl groups, OH groups in the R group, meaning that thing is going to be said to be polar. Then if there are few, we call it to be non-polar. Not only are you going to be seeing carbon, nitrogen, and oxygen and hydrogen, there's some other amino acid that will actually have what? We have sulfur and also iron sometimes. So please take note, don't be confused when you see such. And I'm just saying these amino acids can be demarcated into polar and non-polar. Some other people would also say these amino acids are also amphoteric, meaning they can also be categorized as acidic or basic depending on the nature of them either producing hydrogen ions or hydroxyl ions. So this is just what you need to know, but it's not going to be assessed. The only thing you'll be assessed is in terms of the C terminus, the N terminus, and also the arrangement in talking about the condensation reactions that give off water. So meaning we can break down a sequence of amino acids by adding water, right, to via the process of hydrolysis to produce back the individual amino acids. We're just saying the production of a peptide bond is a reversible process. We can just add water and we get it back. So now remember what we said. If the number of amino acids is less than 30, that particular structure can just be categorized as a peptide, right? What if the number of amino acids is greater than 20? So now I want us to talk about what we call polypeptides, or proteins rather. So if we say polypeptide, so if we say this, so polypeptides are simply proteins which contain more than 30 amino acids, and the first type of polypeptide that we're going to discuss are simply called primary protein structure. So the first type is primary. So under primary structure, we're just going to see a good sequence of amino acids joined or linked together, and this is going to create an alpha chain and a beta chain, so we can have something that looks like this. So let me just give you the correct way of how this guy is going to look like. Yeah, so in a primary structure, we're saying there's a linear sequence of amino acids which are joined by a peptide bond, and of course there are covalent bonds throughout. You're going to see that we're going to have covalent bonds and disulfide bonds. Yeah, so we are going to have something that looks like this. This is a primary structure. These are simply the amino acids just connected like this. It's supposed to be in a good straight line. If I was to show you properly here, so it looks like this. This is how it's supposed to look like. Yeah, they're supposed to be in a linear form. This is how it looks. So this is a primary structure. Then you have the amino subunits given. Now we can have, sometimes you can have covalent bonds, or rather you can have disulfide bonds if a particular amino acid has sulfur in it. So we can have these guys connecting. Rarely though, it only occurs mostly if you have two sequences. So we're saying two primary structures connected to each other. If I put the first one here on top and the other one separate here, they can actually be connected using covalent bonds. Sometimes you can have such a case. Yeah, but rarely, where the guy on top is going to be called the alpha chain, the guy at the bottom is going to be called the protein backbone or the beta chain. That's basically what you have in terms of you having a primary structure. And the best example we can give here is insulin. Insulin is one of the good examples of an example of a protein primary structure. Then the secondary one. So maybe I must mention why insulin is better if it's in a primary structure form. It's because it's easy for us to break it down. It's not complicated. We just have to add water, then all the amino acids will break back into their individual amino acids, then we'll have them separate. So the polypeptide bond, in as much as it contains more than 30 amino acids, but in a linear form or in a primary structure form, it's easy for you to reverse the process with less effort. In a secondary structure, this is a local 3D arrangement of the polypeptide backbone, not the side chain. So we're going to have different conformations. So conformations are just structural isomers, so to say. And we are just having conformations that are going to look like this. This was the linear structure, right? These were two linear structures that I was trying to explain, connected via these disulfide bonds and also hydrogen bonds. So we're just saying we can coil this up, we can just fold it, and when you fold it, it's going to create an alpha helix, and from a beta plated sheet, you can just coil it to produce this. This is a secondary type of structure. So this is important because it's hard for you to break this back. So this is going to be a good form of energy storage, because it takes so much energy for you to break it because of the intensive hydrogen bonds you see in between the two plated sheets that you are given. Yeah, and the perfect example here is the fibrin, like what is found in blood clots, or rather the epidermin. So it's spelled like this. It's found in the skin and also in myosin, in muscles, or rather alpha keratin. So alpha keratin, which is found in hair. Yeah, so two or more of these helices coil together, right, or the supercoiling to form these cable-like structures. That's how we produce these secondary structures. So just pay attention to the bonds. That's the only thing they'll ever assess you off. So what are the bonds that are found in a secondary structure? So the alpha helix is right-handed, meaning it's a conformation that looks like a mirror image, but on the right side of your mirror. That's what we basically mean. Here they're saying 3.6 amino acid residues per turn, stabilized by hydrogen bonds between the first carboxylic and fourth amino group. So this is what they're saying. After 3 amino acids, that's when you see a turn. These turns that you're seeing there, they are only happening after 3 amino acids. That's when we experience them. Yeah, so hope you are seeing that. This is really just for the sake of you understanding. Then the beta sheets, 2 or more polypeptide chains, one if too long, make hydrogen bonding, also called plated sheets because of their appearance. So this is going to either be an antiparallel B sheets or a parallel B sheets, meaning antiparallel, they're in opposite directions, then this means they're in the same directions. The hydrogen bonding in the antiparallel one is more stable as compared to this one, which is a little bit distorted or conformed because it's in the same direction, so it's going to be less stable. By same direction here, we mean the side chains, the guy on top and the guy at the bottom there, they're having the same arrangement, like, because it's like you put valine, lysine, then glycine. Let's say you have something like this. Also down here, you repeat the same sequence. That's what we mean by same direction. Then here, opposite, we mean we'll switch this. You have valine, lysine, and glutamate or glycine. Let me put Y. Then you arrange it here. You start with glycine, then you start with come to lysine, then valine this side. So this is what we mean by opposite directions. Yeah, so apart from that, we can have collagen. This is another example. So all these are just examples. Another secondary structure is the beta plated sheet, in which several plates chains lie side by side. So we can increase the number of chains that we are having. We can even have 3. You can put one there, put one there, put one there. So the more you put the chains or the long strands, the more complex your structure becomes. So this is on the secondary structure. These are just proper examples that you find that they explain in terms of this type of polypeptide bond. So you notice that the intensity of the coiling is just depending on how many strands that you're having. The more strands you have, the more coiling you're going to have. That's called supercoiling. And collagen fibril can be seen to exist like this. In a normal way, at a microscopic level, it's simply supposed to look like this. That's basically how you're going to see the folding. And the next type of polypeptide is simply the tertiary structure. So the tertiary one has the following things that you need to take note of before we even discuss this diagram and explain how these are formed. So when it comes to a tertiary structure, the best way to understand it is to imagine it as just the complete further folding of the secondary structure that you had. Yeah, so it's still going to be in 3 dimensions, but we're now just going to include the following bonds. So this is something you should take away from here. So the tertiary structure will have the following type of bonds. The first one is simply disulfide bonds. So these are very prominent in the tertiary structure. The other one will have salt bridges. So you have salt bridges, and aside from this, you also have hydrogen bonds, just like we saw in the secondary structure. You have the hydrogen bonds, and also you're going to have, this is now going to give us hydrophobic interactions. You're also going to have these interactions between the structures. So by the salt bridge, so in case you're wondering, this is what you're having. You have something like that looks like this. So the hydrogen bonds can be seen whenever you have hydrogen exposed or close to oxygen in another molecule. So this is the hydrogen bond that you're seeing there. Then if there's let's say here you have a disulfide bond, there is a sulfide in another amino acid, and it's close to another sulfide in another amino acid, you're going to see them attracting each other. That's going to create a temporal disulfide bond. Then you can have ionic bonding here. This is what we call the salt bridge. So instead of ionic, we can also say salt. This is what we mean by the salt bridge. And you see that the polypeptide backbone this side is going to curl up in such a way that it's going to expose the hydrogen bonds are going to be outside. Yeah, so if the hydrogen bonds are outside, it means your structure can have two portions which are either hydrophilic or hydrophobic. Yeah, that's basically what you need to see. Yeah, so the internal part, in short, we're just saying the inside part, this part that you see here, let me try to paint it in red. So this part which is hidden inside here is simply hydrophobic, doesn't want water. The side which is exposed outside here, this side here can accommodate water. That's basically what we are saying. Yeah, so this is how the tertiary structure is going to be. Now there's a minimal difference between the tertiary structure and the quaternary structure. So the last polypeptide here is simply the quaternary structure, and in the quaternary structure, from what we have been doing, we're saying we're coming from a primary structure which we can fold two of them, right? We can just fold it like this, then we create a secondary structure. This is what you're going to get. From here we produced a tertiary structure which has those bonds that we're from discussing, which can either give you an alpha helix and a beta, either antiparallel or parallel helix. So you have this. Now when you combine these guys here, you're going to produce a quaternary structure. That's basically what we mean. When you combine multiple sections of these that are held together with by certain bonds. So some proteins are composed of more than one polypeptide chain. Each portion is simply going to be referred as a subunit of the protein. So those tertiary structures that we're from looking at, we can pair them up. We can just combine a bunch of them, and then what we're going to create is going to be a quaternary structure. So this is basically what we have. It's just a more complicated version of something that was initially simple. So these will either have beta chains, the guys on top there, or they'll have alpha chains at the bottom here. So this is basically what you have in terms of proteins, the polypeptide proteins, the classes if we were to classify them. Yeah, and hemoglobin is a better illustration. And of course, the other things that you have to learn in terms of the disadvantages of not having enough proteins, this sometimes, so cells blocking capillaries are rapidly destroyed, and the loss of these hemoglobin molecules can cause anemia sometimes. And also, there's also, of course, there's sickle cell anemia, but there's, let me show you here, there is lack of proteins, in particular collagen, which was a secondary structure, sometimes can cause the following disorders. So sometimes you can get this, or the common one, which is scurvy. This is what you can get if you lack collagen. Yeah, so these, of course, these are biomedical consequences of having insufficient proteins, which they will not ask you. Of course, this is just for your own information. So a summary of what we are from discussing, the summary here is that we have we have proteins that are primary. The number, they are the numbers of sequence that you're going to get. So for example, if you have there's a portion that sometimes you can have certain calculations. They'll ask you the number of possible arrangements of what you have. If I give you 8 amino acids, if I was to give you 8 of them, to say how many ways can you arrange these guys, so you just go by getting 8 factorial, right? Now, if there's a limit to what you can get, for example, if we have 8 amino acids and the protein that we should call for can only be coded or be summoned if you arrange 3 things. So we're just going to say 8, choose 3. How many ways can we choose 3 things from 8 things? So there's that as well. So there's that mathematical aspect of that. Yeah, some people say the number of ways sometimes could be, if you just need to call 2 things or 2 amino acids, you can say 2 to the number of amino acids that is present. We'll talk about this later in the discussion of your tutorial sheet. But here we're saying primary, we said it's just a sequence, a linear sequence of the amino acids, mostly joined by the peptide bond, which is also going to be called a covalent bond because you're having much sharing of electrons. That's what you have. Water is given out. This is a condensation reaction. Primary, we're just saying we are best going to describe this as a structure that has an alpha helix and beta plated sheets, which can either be parallel or unparallel. So they contain hydrogen bonds between the members of the peptide bonds. Then we have the tertiary structure, which is the folding and twisting of the polypeptide. Only one polypeptide is present, right? Only one chain. But if we put more than one chain, we now produce a quaternary structure, which is going to have those random hydrophobic, hydrophilic, and we have those disulfide bonds and everything else that we discussed. So this hope gives us a summary. Now we're saying these can actually be denatured, and whenever proteins are denatured, they lose their shape, they lose their functions. A best illustration is what we discussed under enzymes, to say enzymes, since they are protein in nature, there is a limit in terms of temperature where these enzymes can have optimal activity. Yeah, so once you exceed that optimal temperature, meaning that protein in nature enzyme is going to be damaged, or rather denatured, meaning either the active site or the shape has been distorted. So now it cannot carry out its function. So it's just a general application to say enzymes, since these are produced by the body, there's a limit to the temperature that we can expose them to. The conditions of the reactions are supposed to be limited. Yeah, and also this applies also in terms of the pH. So every protein has a limit in terms of the pH that it can work within. Yeah, so that's basically what we have. So this wraps up everything you need to know under proteins. So feel free, in case you have any questions, to ask on WhatsApp. The number is there on the YouTube channel. Thank you so much for your time.